morning, good afternoon, or good evening, ladies and gentlemen. I hope you are doing well today, and welcome to lesson 8.4, which is called Ohm's Law. We are continuing with our discussion about electric charges, and today we're actually moving more into our discussion of electric current, which will lead into circuits in the next couple of lessons. So without any further ado, let's jump right into it. First, a quick review. Remember that every charge, which we can designate with the letter Q, is surrounded by an electric field. This electric field determines the amount of force exerted per coulomb on other charges. The electric force between charges creates potential energy, but we can generalize that potential energy and just call it electric potential. So each charge has electric potential surrounding it, which varies with distance from the charge. So if we just have a single charge of, say, positive 2 millicoulombs, then we can calculate that at a distance of 15 meters, the electric field strength is positive 8 times 10 to the 4th newtons per coulomb. And you can calculate that using the formula K times Q divided by R squared, where K is equal to 8.99 times 10 to the 9th newtons times meter squared per coulomb squared. We can also calculate that at a distance of 15 meters, the electric potential is positive 1.2 times 10 to the 6th volts, or joules per coulomb. So these are both quantities that are independent of a second charge. It doesn't matter what charge we place here. These two quantities will remain the same for a distance of 15 meters from this charge. Now let's suppose that we do go ahead and add a second charge, this time a positive 3 microcoulomb charge. Now that we know the magnitude and sign of this second charge, we can go ahead and calculate the amount of force that is acting on the charge, which is K times big Q times little q divided by R squared, and works out a positive 0.24 newtons, indicating that the force is pushing away from this charge over here. And we can also go ahead and work out the potential energy of this charge, which is positive 3.6 joules. So once again, electric field and voltage can be calculated without a second charge present, but electric force and potential energy, those require two charges to work them out. Okay, also recall that around the positive charge, the potential is highest when you are close to the charge, and it gets lower as you move further away from the charge. And positive charges always have a tendency, if they're free to move from high potential to low potential. Negative charges, on the other hand, tend to move from low potential to high potential. And if the fixed charge happens to be a negative charge, the low potential is close in and the high potential is further out. And again, positive charges that are free to move will move from high to low potential, which in this case means they will just move towards the negative charge, and negative charges will move from low to high potential, so they will move away from that fixed negative charge. Alright, now that we've covered all that, which was basically just a bit of review from lessons 8.1 through 8.3, please go back and check those out again if that was all completely foreign to you. Let's talk about what a conductor is. And no, I don't mean the guy that drives the train. A conductor is a material that allows the movement of electric charge, so metals are going to be conductors. Whenever you apply an electric potential to a conductor, it will cause electric charges to move through that, and in most cases those electric charges are going to be in the form of electrons. Remember what we said previously, atoms are made of protons and electrons, and the protons are pretty much locked in place. They don't really get to get out and move around, but the electrons can come and go. So here we have two objects with some electric charges placed on them. One is a rubber balloon. Rubber is not a good conductor. It's what we call an insulator. So when the electric charges are placed on the balloon, they tend to just kind of stay where they are. They're not going to spread out and move around the balloon. On the other hand, when you put electric charge on a metal sphere, the electric charge will tend to spread out and try to get as far away from each other as they can, so they will spread out all around the surface of the sphere, and this is possible because metal is conductive. Now watch what happens when we bring an external negative charge close by to this balloon. The charges don't really move because they can't. Again, rubber is an insulator, so those charges are kind of just stuck where they are. But watch what happens when we bring the same negative charge close to the metal conductor. All of the negative charges on the metal are repelled by this external negative charge, and because metal is a conductor, they are all able to move freely, and so they will bunch up on the opposite side of the metal from the external negative field. Voltage, or electric potential, gives these charges potential energy. It's what causes the charges to flow. The bigger the voltage, the more the charges will tend to flow. In fact, in many cases, we refer to voltage as electric pressure. So you can think of it like the pressure in a water pipe. The pressure in a water pipe is what forces the water to flow through the pipe. Well, the voltage in a conductor is what forces the electric charges to flow through the conductor. So it's analogous to pressure in a water pipe. Next, let's talk about resistance. So resistance is how much a material resists or prevents the movement of electric charge. Conductors, like metals, tend to have a very low resistance because they allow electric charge to move through them more or less freely. On the other hand, non-conductors, or insulators, materials like plastic, glass, and rubber, tend to have a very high resistance value. The symbol for resistance is a capital R, but its unit is an ohm, O-H-M, and this is from the same person that we get Ohm's law. And the abbreviation for ohm is a Greek letter omega, which sort of looks like a horseshoe, or maybe a person's head and shoulders, whatever you think it looks like. But practice drawing that a few times when you get a chance. This is the Greek letter omega. And as far as I know, I could be wrong on this, but as far as I know, ohm is the only quantity that we use that uses a Greek letter for its abbreviation. So that's a bit of trivia for you. Let's talk about the resistance of different wires, since, we're going to be moving into talking about circuits, so we will be discussing wires a whole lot. Obviously, the resistance of a metal wire is going to be much, much, much less than the resistance of non-metal materials. That's why we don't make wires out of things like plastic or rubber. The wires may have plastic or rubber coatings to prevent electricity from flowing where we don't want it to go, but the core of the wire is always going to be a metal because we want the wire to have very low resistance. A short wire is going to have less resistance than a long wire. It just makes sense. The more material a charge has to flow through, then the more resistance it encounters along the way, even if the wire is made of metal. A thick wire will offer less resistance than a thin wire. Think of it like a freeway. A freeway with, 6 lanes is going to allow much more traffic to pass than a backcountry road with only 2 lanes. This is assuming, of course, that they're not constantly doing road construction. Looking at UI-40. And finally, the resistance of a cold wire is going to be less than the resistance of a hot wire. As a wire heats up, its resistance increases. Speaking of current, let's get a formal definition for that. Current is the rate at which charges flow, and it is directly proportional to the potential difference, which means if you increase the voltage, you will increase the current, but it is inversely proportional to the resistance. So if you increase the resistance, you will decrease the current. Now, the symbol for current is a capital I. I don't know why. It just is. And the unit for current is an ampere, or sometimes we just say amp for short, and it's abbreviated with a capital A. 1 ampere is equal to 1 coulomb per second. So if a wire has 1 amp of current flowing through it, then that means that 1 coulomb worth of charge is passing through that wire each second. So this is Ohm's law, the purpose of this whole lesson. We have finally reached it. The relationship between current, voltage, and resistance. The current in a wire is equal to the voltage divided by the resistance. That's a nice, tidy little relationship for you there. These two graphs show the relationship in visual terms. If you keep the resistance constant and slowly increase the voltage, then the current will also increase in a linear fashion, which means if you double the voltage, then you will also double the current, as long as the resistance stays the same. However, if you keep the voltage the same and slowly increase the resistance, then the current will decrease. If you double the resistance, then the current decreases by 1/2. And this is what happens in a dimmer switch. If you have a light in your house with a dimmer switch where you turn the knob to make the light brighter or dimmer, what you are doing when you turn that knob is essentially adjusting the resistance. So the more you turn it in one direction, the resistance increases, the current decreases, and the light becomes less bright. If you turn it in the other direction, the resistance decreases, the current increases, and the light becomes brighter. So we have a couple of skill practice questions to finish up this unit, and let's go ahead and take a look at these. First up, what current will flow across a 40 ohm resistor when a potential difference of 400 volts is applied across it? This is a simple little plug and chug problem using Ohm's law. Excuse me. I is equal to V divided by R. We'll plug in the numbers that we know. We know the voltage is going to be 400 volts, so we will put that on the top. And the resistance is 40 ohms, and so we will place that on the bottom. Omega symbol. And the math is pretty simple. 400 divided by 40, well, that's just 10. Get three significant figures, so I will at 10.0. And since we are solving for current, we will use the unit amps. And that's it. And our second and final skill practice question. It says, across what resistance will a potential difference of 90 volts cause a current of 30 milliamps? So we must be careful. These are not amps, they are milliamps. MA. So we'll have to think about, what does milli mean? All right, we will start with Ohm's law. I is equal to V divided by R, but we are not trying to solve for I, we are trying to solve for R. If we multiply both sides by R to get it out of the denominator, then we have I times R is equal to V. And if we divide both sides by I, so we can get R by itself, then we have R is equal to V divided by I. So we will plug the voltage on top, and that's going to be 90.0 volts. And then we will put the current on the bottom. It's 30 milliamps. So we will put 30.0, and then milli means times 10 to the minus third amperes. You pull out your trusty calculator, you say 90 divided by 30 times 10 to the minus third. Make sure you include that times 10 to the minus third. The answer is not 3, it is 3,000. And since we are solving for resistance, it is going to be 3,000 ohms. And folks, that is truly the end of lesson 8.4 Ohm's Law. Thank you very much for your time and attention. Please head on over to Google Classroom, and I will have a very brief assignment for you there. Come back tomorrow where we will be going into lesson 8.5. We will start talking about electric circuits. You ought to get a charge out of that. Until then, keep washing your hands, take care of yourselves. We'll see you tomorrow. Bye.